another metric that I don't think we track right now, which is unconfigured users. So we keep track of the software.
All right, so that's the last session for today from Nícolas, Rethinking Device Support for the Long Term.
Okay, so hi everyone, my name is Nícolas, and today I'm going to be presenting about how we can rethink the device support for the long term. So first of all, I work at Collabora, and what I do there is I do the upstreaming of the kernel support for some Chromebooks, and also I improve the coverage for KernelCI, so adding new tests. So first of all, why is upstream the upstream support relevant? So well, there are many reasons, and most of you probably know very well about them. But basically, for one, when you have good upstream support for a device, you can count on continuous updates, since it's easier for the OEMs that are developing the device. If they're basing their work on upstream, it's easier to continuously rebase and provide more frequent supports, more frequent updates for the device. Also, for the same reason, you have less of a vendor locking problem, because you don't need to rely on the downstream kernel for the device. So you can just install the mainstream kernel and be happy with it. On the OEM side, also there's lower maintenance cost, so it's also a good there's a good benefit for them as well. And so like basically in the end you just get like a longer lifespan for the device. So, and that's what we've been working on the upstream support for these Chromebooks, and so that's what's happening. So as we're focusing on the upstream support, these devices are basically staying longer on the market and getting a longer life, having more updates. So, but of course, like we have new devices every year, and so the demand isn't going to diminish. So basically, as I see it, as we get these devices living longer and needing more updates, and there are more devices out there, basically it's a problem of scale. So that's why continuous integration is important, because it's the way we're going to be able to automatically detect regressions and basically keep up with this demand. And it's also important to emphasize that enabling tests earlier in the device's life is important, because basically there's a cost in enabling tests, and if you do them the earlier the better, because then you get to benefit more from that over the device's lifetime to get the regressions. So a little bit about KernelCI itself. So that's why we need a CI, and in the case for the kernel, we have KernelCI. The main instance is there on linux.kernelci.org, but there are also that test the upstream kernel. But there are also other instances, like the one on chromeos.kernelci.org that runs the TAST tests, and not only on the downstream Chrome OS kernel, but also on the upstream kernel. So the way the KernelCI works, basically, it's this pipeline. So there are several Git branches from Git trees that are monitored, and when a new revision is found, the jobs are triggered that will build the artifacts, which means like the kernel, the modules, device trees, and the rootfs for the test. Once you have that, the test itself is going to be queued to run on a device in a Lava lab with pointers to those artifacts. And after the test after the test runs on the device, then the results are going to be pushed back to the dashboard in KernelCI, so they're available for anyone to check out. And if there are any regressions detected, they'll be reported to the KernelCI results mailing list. KernelCI can be configured through several YAML files, and like for most people, that's the part you're most interested in. So, for instance, there's a build configuration that's where you set the branches and the trees that will be tracked. Also, the config fragments that will be used as part for the kernel build, compiler versions and whatnot. So, for instance, some maintainers have a for KernelCI branch on their. They have a for KernelCI branch on their tree and also register that in KernelCI, so that they can, as they receive the patches, they can merge those patches to that for KernelCI branch and have them run on KernelCI before they actually, so they can validate the changes before they actually merge those to their main branches. There's also a lab configuration where the labs themselves, so the Lava labs that have all these devices on racks, like running the tests, there are currently around 11 of them. Also, you can set filters there, so you can filter out whatever kind of test you don't want to, or you want to run on your lab. There's a rootfs configuration where you define what rootfs is going to be used for the test. So you can add a custom rootfs there, which will be involved like setting the base OS itself, so the Debian version and so on, like architecture packages that will be installed, the scripts, because like you might want to do some extra tweaking before you run the test. Maybe you might want to compile something from source, and FS overlays if you need some special file in your rootfs. And finally, you have the actual test configuration where you define the tests themselves, so the test plans, which rootfs the test needs to run, which Lava job template, which is the actual file that gets submitted to Lava to run the job. Some parameters that might be needed, and the device types, which are the actual devices that are getting the test run on. There are currently around 208 device types in KernelCI. So basically, it's simple for anyone interested in improving the coverage for KernelCI to add a new test or add a new rootfs. If you have some of your own devices that you want to run tests on, you might add your own lab there. So these are the tests that are currently available on KernelCI. The baseline tests are very interesting ones. I think they're simple tests, but they do a lot. So basically, it uses the bootRR suite, and basically that has a generic and a machine-specific part. But the point of this test is to make sure that the basics are there, so that as the generic, for the generic part, you have things like checking that no devices are deferring probe, so the machine is actually probing everything that it should. And for the machine-specific parts, you can check like whether all the devices and all the drivers that you expect to be there are actually there and up. So yeah, and like we have lots of other tests like k-self tests. There are multiple of them. LTP. You have decoder conformance tests that runs Fluster to verify that the output of a decoded frame from a hardware decoder matches what it should, and stuff like that. So IGT, for L2 compliance, libcamera, which is one I added, for the Chrome OS embedded controller test, sleep test to test suspend resume, and that kind of stuff. So we have there. So that's about it for the basics for KernelCI that I wanted to share. So during my work in Collabora, I was doing the upstreaming for the support for the Acer Chromebook CB514, which uses the MT8192 SoC from MediaTek and the Azurata baseboard. And during doing the upstreaming for the support for this machine, I had to obviously test all the components from the machine, and if I found any issues, I would fix them and send them upstream. But since the kernel is a moving target, I had to basically redo this every time, manually, constantly, on every rebase. And I did detect several issues during the upstreaming process. And of course, like if these tests, there are some tests in KernelCI that could have enabled this to be done automatically without me doing them manually as I was doing the upstreaming. So to give some of these examples, these are actually the commits that me and a colleague, we sent upstream to fix the issues themselves. So like you have things like for those two first commits, like the issues that they fixed, they were preventing the display from probing at all. And on this machine, on the machine that I worked on and a few others from MediaTek, and basically that's those kind of issues like the display not probing, that can easily be detected by a baseline test or IGT KMS test, which would fail if display isn't probed. Also, you have another issue where there were basically the call to disable vBlank was moved to a wrong place where it was the vBlank interrupt was being disabled before it should, and that caused warnings during suspend, and that can be detected by the sleep test that does a suspend resume cycle. And you have also the other issue where the encoder stopped probing as well because of platform get resource being deprecated on this platform. So that's also something that could have been detected by a baseline test. So where are we now for this machine, KernelCI? I have worked on upstreaming enabling the configs. So I added the config fragment in KernelCI to get all devices probing and working on this machine, and also upstream the dev config. It's already queued for the next release. Also enable the baseline tests that I talked about. So the baseline tests for this machine are already running in KernelCI. And I added the device probe checks for the machine itself in baseline. But there are still lots of stuff to enable, like the also key self-test, which I'm working on right now. This machine makes use of, it has more complex controls, so the UCM needs to be applied before the tests are run, so all the paths can actually be tested, the auto paths. And some other tests like cross-EC, lib camera, referral to compliance, IGT KMS, to name a few. And there are also some tests like referral to decoder conformance that can't be enabled yet because the upstream support hasn't quite landed yet, because it depends on the description in the device tree for the hardware decoder. The patch is still being reviewed in the mailing list. And same thing for SLIP, which requires a CPU frac node, which isn't there, and the GPU also isn't there for this machine yet. So after those components get enabled upstream, the tests can be enabled so we can catch those issues when they happen again. This is a screenshot of the KernelCI page, the dashboard, with the results for this machine. As you can see, there are a few tests that are failing because when I added this baseline test, I already added the checks for the devices for all devices, including the ones that haven't made it upstream yet. So the one that's failing there, for example, is for the external display for this machine, and it isn't probing because upstream there isn't yet, the support isn't enabled. So as it gets merged, those tests will start passing. And if they ever start failing, then we can quickly notice that something broke. So where can we grow KernelCI from here? I think definitely more subsystems should have more coverage. So maybe like IIO and input are subsystems that I didn't find any tests to run. So I think as we increase the coverage of the subsystems, we'll start catching these issues. If we don't have the tests themselves, like we can't detect when the issues happen. And while baseline tests are like they already help with the base support, like we really need these specific subsystem-specific tests to detect that issues in the usage of the hardware components themselves happen. So besides that, also more trees from maintainers. So if there's any maintainers in this room that would like to have some branch tested by KernelCI, maybe send a pull request in the KernelCI repository or get in touch. So we can start testing more of the trees before and catch the issues. Also, more labs, of course. So basically, we rely on the labs with the devices on them to run the tests. So the more labs we have, the better, with more diversity of the devices. Maybe you're interested in some device that isn't already present in some lab. In that case, it would be interesting if you could set your own Lava lab with the devices you're interested in, and hook that up to KernelCI so that you get to benefit from the tests that are already there, and they get run on your lab, on your devices you're interested in. We could definitely also have more of the K-self tests, LTP tests added to KernelCI, and also support for KUnit, which as it grows in the kernel, it would be great to have support to run those tests. So basically, I think that there's still a lot to be gained from the open source model we have in the kernel that we're all pretty familiar with in the development sense, where not everybody does everybody does a little bit of work, and also everybody gets to benefit from it. I think we're still starting to see that in the Linux testing side of things for that. So as we keep increasing the branches, the code base, the device coverage, everybody will start to benefit from that. And this usage of the KernelCI will allow us to have to be able to cope with the quantity of devices that are there, and respond quickly to the regressions as they happen, and because of that, be able to give a actual reliable long-term support for all these many devices, and and everybody will benefit from that. So, and that's about it for the presentation. So, if you have any questions.
Thank you. Are there any questions? Seems everybody is eager to get out. So thank you for the talk. Thank you all for being here. This was the first iteration of the kernel dev room. We hope to make this a regular thing at FOSDEM, so spread the word. We can use loads more submissions than we had, although we had a lot of great talks. I really want to thank, we organized this together, like 3 people, Stefan Graber from Canonical, LXD team leader, one of the eBPF Upstream maintainers, Daniel Borkman from Isovalent, and I'm Christian Browner. Thanks, everyone.